Hi. So let's move on to variance part. Uh, oh, sorry. Should have this one. Okay, this one. So the ratio estimator is a nonlinear smooth function of two random variables, and these two random variables is x bar and y bar. So that's why we write it as a something like this function. So this is a two random variable, and this is fixed. And the and then the idea is, in general, we cannot compute the exact variance of this nonlinear estimator. However, we can obtain an approximate variance by applying a linearization method. So what do we mean by linearizing? So linearizing means that we can approximate it as a linear function. So something like this. So this is linear, right? So once you do that, then the variance, then we know how to compute the variance of this guy, right? So that is the idea. Uh, so this operation, so that is a linearization. Uh, and a mathematical tool for obtaining this linearization is Taylor method. So Taylor linearization method, and this is the formula for Taylor expansion. Taylor expansion. So basically we expand. So this is a function of two argument, and we basically expand it around the mean of the two argument. So as a linear function. So the first one is just to plug in the mean, and then take the partial derivative with respect to the first component, which is x, and then evaluate it, and then this is kind of a tangent, right? With respect to x, and then the other one is the tangent with respect to the second component, which is y. So this is the general formula, and then question is how this linearization. Okay. So this, if I use for this particular f, right? So for this particular f, how will this number be? So see, so f, x, and y is what? X bar times u, y given x, right? So that is the from this definition. So this is a definition of f. From this definition, we can write it this way. And so you can, you can compute it. Then this one is x bar u and y bar, y and x square, right? And then minus. And if you take the differentiation, then there's no minus. So that means if you plug in to x bar u, y bar u, then u, y bar u divided by x bar u square. So that is minus y bar u divided by x bar u. Okay. And also f x bar u, y bar u is x bar u times 1 over x bar u. So that is 1. Therefore, the linearization here can be written as x bar y bar is fx by u, y by u. So okay, y by u plus this guy, the first guy, right? So I'm gonna just write it. So that is linearization x bar minus x bar u plus y f x bar u y bar u y bar minus y bar u. So that means if I plug in x bar u times y by u divided by x by u plus minus y by u divided by x by u times x bar minus x by u plus 1 times y bar minus y by u. Okay, so then that leads to y by u cancels out, so y bar minus r. Okay. Oops, sorry. I should let's write it y by u plus y bar minus y bar u minus x bar u. So the point is this guy, okay, this guy is r. No, b. We wrote it b. B. And so that we write it b, then it's b times x bar minus x bar u, which is y bar u plus y bar minus p x bar. Okay, so that is this result here. Okay, so the main message is y bar r is so the main, this is the main result. Okay, the main result is this. Y bar r is approximately equal to y bar u minus x bar y bar minus p x bar. So r equal to approximately equal to y bar plus px bar. So the variance of this guy is, this is constant, so it doesn't really matter for the variance. So we have only to worry about this part. Okay. So now, what is this? Y bar minus p x is 1 over n summation. Okay. So 1 over n summation I equal sum yi minus p xi. So we can call it as a di. So you can call it as a di, and then it's just the sampling variance. So f is n over n, and so variance of d bar, right? Essentially, that is 1 over n, 1 minus 1 n over n, s ds square, and s d square is this. Okay. By the way, d bar u is summation. D bar u is 0 because the summation of di is d by u equal to I equal to 1 to n yi minus pxi, and this is 0 because b is y by u divided by x by u. Okay. So that's because this is 0, we can write it this way. So that is the formula for variance. Okay. Now, let's compare the variance of y by r. So question is, okay, when we have this one, so when the variance of y by r, the ratio estimator is less than or equal to the variance of the sample mean. So the first one basically sy square, and that is the 1 over n, 1 minus n over sd square, right? So we have only to compare when sy square is less than or equal to sd square. So sd square is this guy. So this guy. So basically you have only to compare I equal to 1 to n yi minus y by u square, compare, okay, let's write it one by one, p xi square. And now you can write it as u minus b xi minus x bar u square. So you can expand it like this, yi minus sy by u square plus p square xi minus x bar u square minus 2 covariance right? So this one basically, if you okay, it's the same as sy square is equal to sy square plus b square sx square plus minus 2 times b covariance sxy. Okay. I guess I will write it in the next page. You can check the detailed algebra actually in the script that I uploaded. But anyway, sy square sd square is equivalent to sy square minus plus b square sx square minus 2. So it's a really tedious algebra, right? So that means minus 2 p sxy plus p square sx square is less than or equal to 0. Sxy is less than or equal to 1 over 2 sx square b. So that is actually, you can write it as then you have some algebra x bar u divided by, because b is y by u x by u, so sy y by u. So that is the half of CV x divided by CVY. CV is standard error, I mean standard deviation divided by expectation. So CVX is a standard deviation divided by mean, which is this one. So so main message is, so that means this is correlation, by the way, correlation. The main message is that the ratio estimator is efficient. I mean, similar. The variance of ratio estimator is similar than the variance of the simple mean, if and only if the correlation is reasonably high, so higher than this quantity. Okay. So roughly, if you CVs are all x and y's are equal, then means the correlation should be greater than or equal to 0.5. Otherwise, it doesn't help. Okay. Now let me quickly finish up with the variance estimation. So note that the variance of the y by r is 1 over n, 1 minus f, and f is this one, right? St square. And St square is the population mean of the population variance of di. So you can estimate it. So the one way to estimate this guy is we had, so you have only to estimate SD. So how to estimate this one? Well, you can estimate SD, small SD square using sample, right? So you can do that. Oops, Ti minus T bar square, so something like that. But the problem is that you don't observe D, because Di is Yi minus Bxi, and we don't. B is a population parameter. So you don't know. So the idea is, okay, since we don't know D, we can estimate it by Ti hat, and we call it Ei. Okay. So then you can so the basically formula is that you use Ei, which is kind of residual, P hat Xi, right? And use this to compute the sample mean, sample variance. And now you can check that this guy is 0. So this is just you have only to use this as a square. So that is the variance estimation.